So salt marshes are some of the most productive, the salt marshes of the southeastern United States are some of the most productive ecosystems in the world. They act as strongholds of biodiversity and provide essential habitat for a variety of marine organisms, including nursery habitats for many commercially important species. Additionally, these ecosystems protect our coastal communities from the impacts of hurricanes. Simultaneously, they act as carbon sinks, sequestering vast amounts of carbon and greenhouse gases from our atmosphere while also filtering pollutants from the environment. However, our salt marshes face increasing pressure due to an explosion of coastal population in recent years, bringing with it unfettered growth and urbanization, which ultimately impacts the health and quality of our salt marsh ecosystems. By examining the groundwater characteristics and flow in this environment, we can kind of keep a finger on the pulse and examine the overall health and stability of the salt marsh. The particular boundary that's been traditionally understudied is the Barrier Island Maritime Forest and Salt Marsh boundary that we're looking at here today. This is characterized by fresher groundwaters flowing from the barrier towards the salt marsh, and on the reverse side, more saline estuary groundwaters pushing up to the barrier island as a result of tidal forcing. This creates a subterranean mixing zone where you have a variety of nutrient and salt and salinity regimes that influence what kind of plants can grow in the salt marsh here. So, electrical resistivity tomography is a technique that we can use to investigate these different soil and groundwater regimes based on their resistive properties. We can couple this with more traditional groundwater investigation techniques, such as monitoring the water level monitoring the water table height, in addition to actually physically sampling our groundwaters through groundwater wells. Together, we can couple these to make a more clear picture of how groundwater flows across this interface. By taking monthly measurements, too, we can also examine how groundwater flow interacts with various hydrological drivers, such as increased precipitation or droughts and hurricanes and tides. By conducting this study on a relatively undeveloped barrier island, such as Wadey's Island, we can also create a baseline for which to compare to different sites around the country. On these more anthropogenic and human-modified sites, we can have various nutrient and hydrological differences, such as inputs from stormwater runoff or septic tank drainage fields that would impact your biology in the salt marsh. You can also have geology that's disturbed from the building of roads, home sites, and seawalls, which all affects how groundwater flows here. In more remote settings, too, a lot of communities use this surficial aquifer for their drinking water and agricultural purposes, and with sea level rise due to climate change, this could face salinization and sea level and saltwater intrusion. This research aims to link the scientists and the community planners together to create really resilient coastal communities that can withstand the impacts of climate change on our hydrological system, in addition to preserving our salt marshes and mitigating the impacts and stress that they face. Thank you.